So how is it possible that the CPU managed to run a more complicated program in the same amount of time? To understand that, we need to refine our model of CPUs one more time. Because in a modern CPU, there's not just one minion sitting there. Even on a single-core CPU, you should think of there as being multiple minions waiting to do work all at the same time. You don't have to write this into your program or into the assembly code that you generate from your C compiler, say. The CPU figures out that it can do certain things all at the same time, all by itself. For example, here we see that the instructions to execute include moving a value into register X9, X1, and X8, and all of those moves are independent from each other. So the CPU can have a different minion work on each of those all at the same time. Even this branch can be done at the same time because it depends only on X2, and that register is not being modified by any of the other registers. So when the CPU is ready to execute this sequence of instructions, it'll fire off, let's say, 4 minions to work on all those pieces. In this case, we did a branch, and our minions move on to the next set of instructions. And in this case, we have a branch right away, and so perhaps these other minions can't get working on these other instructions because they don't know whether they need to work here or will be needed where the branch jumps to instead. So perhaps this minion works all by itself, and then we discover that we do need this next sequence of instructions right after the branch that wasn't taken. So a minion can be allocated to this load instruction, and another minion can be allocated to this sub instruction here. This load and the subtraction, they're independent because the load is moving into X2 and the subtraction is working with X3. These two instructions, though, the add and the multiply, they could have minions associated with them, but they can't run just yet, it seems, because they depend on X2 and they need the value to be fetched by this minion first before they can run. So maybe they just hang out for a moment and wait, while this minion nevertheless can proceed even though it's a later point in the program. And that's one of the surprising and potentially confusing things about how a CPU actually works. We can run things later, but these data-dependent instructions need to wait for the earlier result. So let's say the minion here in blue does load into X2. Now these two minions can be allocated to these two independent instructions, right? They're both setting X9 and X1, both using X2, but neither depends on each other. Meanwhile, the orange minion can move on to the branch, and now the blue minion maybe just hangs out here because we need to know which way the branch is going. The fact that these additions and multiplications can happen in parallel, in fact, explains why, even though we added multiplication to our program, it didn't change how fast it ran overall, because we added multiplication that was just working at the same time that the addition was working anyway.